Welcome to our lecture series. Today we are receiving Professor Jefferson Almeida Gomes from the University of Aberdeen in Scotland. Thank you very much for accepting our invitation. Dr. Gomes got a PhD from Imperial College London, 2004, following an MSc in Applied Mathematics at the State University of Rio de Janeiro, 1999, and a BSc in Chemical Engineering from the Federal University of Rio de Janeiro in 1996. Prior to joining the University of Aberdeen, Dr. Gomes was a research fellow at the Earth and Sciences and Engineering Department in the Imperial College London and acted as a scientific consultant for a number of international energy companies. He will present his talk, Multiscale Models for Energy and Environmental Systems. Bem-vindos ao nosso ciclo de palestras Ambihidro. Hoje receberemos o professor Jefferson Almeida Gomes, da Universidade de Aberdeen, na Escócia. Agradecemos muito por aceitar nosso convite. O professor Gomes obteve seu PhD no Imperial College London em 2004, depois de um mestrado em Matemática Aplicada na Universidade Estadual do Rio de Janeiro, em 1999, e um bacharelado em Engenharia Química pela Universidade Federal do Rio de Janeiro, 1996. Antes de ingressar na Universidade de Aberdeen, Dr. Gomes foi pesquisador no Departamento de Ciências da Terra e Engenharia do Imperial College de Londres e atuou como consultor científico de várias empresas internacionais de energia. A seguir, ele vai apresentar sua palestra Modelos Multiescalas para Sistemas Ambientais e de Energia.
Good day, everybody. My name is Jefferson Gomes and I'm from the University of Aberdeen, the northeast of Scotland. And today I will be talking about multiphysics, multiphase and multiscale modeling applied to the energy and environmental sectors. Before I start, I would like to thank the Instituto Federal Fluminense through the ciclo de palestras da AMB Hydro for inviting me for this to give this talk, and in particular I would like to thank Professor Jadel Gon and Professor Antonio Silva Neto. I'm quite honored to be here today to talk about my research. I've known both of them for quite a long time and I hope everyone enjoy this talk. So before I talk about my own research on numerical modeling, I would like to introduce the University of Aberdeen. The university was founded in 1495, so 5 years before the first European arrived in the Brazilian shores. It's the third oldest university in Scotland and is the fifth oldest university in the whole UK. We are actually northeast of Scotland. You can see here almost same latitude as Moscow in Russia. It's a beautiful campus, very sunny when in the summer. It's very enjoyable to be there, to be here actually. The university has 5 Nobel laureates. It's ranked one of the top universities across the world, has a large number of students from everywhere in the world. So it's a very international university. International relations is something that we are proud of. A large number of students, just around 16,000, but these numbers are from 2 or 3 years ago. But with this situation nowadays, we don't know exactly the numbers that we are now. But it's not just sunny, because your northeast is Scotland. Cold is our first nature, the very first nature, and when it's cold, it's really cold. You can see here 3 beautiful pictures of the main part of the campus. So what you see here is the university chapel, which is part of the oldest building, which is one of the oldest buildings in the campus. Within the university, there are several different schools or colleges. So the College of Medicine, Dentistry, etc., and the College of Physical Science, where I'm based. In this college, there are 3 major schools: engineering, geoscience, and natural and computing sciences. Within the School of Engineering where I work, there are 5 research groups, and they are really top-notch around the world. And I work at the mechanics of fluid, soils, and structures. Because our position in northeast of Scotland near the North Sea, we have very strong links with the oil and gas industry, and therefore most of the school actually were developed toward this industry. However, over the past few years, the past 5 years, the portfolio of the university and of the school has changed significantly, and now we're have a strong focus on renewable energy. We also have strong work on sensor network technology, drilling technologies, cement, and carbon capture and storage. The university or the school is known by its world-class facilities on environmental and hydraulic fluids. It's a huge experimental facilities that are used by several of our staff and people from everywhere in Europe. But Aberdeen is not just a university. And so we are based on what we call Old Aberdeen, so the older part of Aberdeen. But around Aberdeen, so Aberdeenshire, there are several good places to go. So beaches, stunning beaches, cold but really beautiful. Aberdeenshire is known by the number of castles, so it's one of the largest densities of castles and castle ruins in Europe. The oil and gas industry is present in our daily lives. And finally, we cannot talk about Scotland and not talk about whiskies. There is a large concentration of whiskey distilleries in this region. We are basically at the highlands. So now come back to science. Let's talk about science. Let's give a motivation for this talk. So when we talk about energy itself, the first thing that comes to our mind is switch on and off lights, turn on and off your mobile phones, TV sets, and etc. So electricity is part of the energy, but it's not just electricity, but also transport and resources for other materials. So there are different sources of energy as part of our energy matrix. So from geothermal on offshore wind to nuclear, hydropower, tides and waves as a renewable energy, coal as a node and very pollutant energy source, and oil and gas reservoir. So all of these are part of the energy matrix. In some places, one energy matrix is more important than others, but in general, this is the energy matrix that we have today. As a society, we are very focused on generating power from fossil fuels. So we have here a coal power plant and a natural gas power plant. They produce a good chunk of power across the world, but at the same time they contaminate the air and contaminate the soil and contaminate the water bodies. So we have now to change into renewable. So I think this is a constant across societies. The problem is how we move from fossil fuel based to renewable based. We require new technologies to make sure that the renewable energy is reliable, efficient, and can provide energy at a good price. So we want to change from fossil fuel to renewable, mostly because they impact the environment. But when you make this transition, or when you're going to make this transition, there will be an impact on the economy, and you need to mensurate, you need to quantify this. There is also another aspect that is important when you talk about energy transition: retrofitting existing systems. So part of these units here, part of the units that use nowadays for fossil fuel, can be retrofit to be more environmental friendly. If you can, how? So these are some of the challenges that we have today. But not only this, energy and environment are part of energy and environment are part of the same game. And what I have here are a few issues when we talk about energy and environment. So for natural disasters, that some people claim that's basically because the heating in the world nowadays, climate change. Accident scenarios, for example, here's a core melt of Chernobyl, a reactor accident in offshore facilities, so that's from the horizon, Mariana, so everyone heard about, and pollution in our cities. All of these need to be managed. So models, advanced models, multiphysics and multi-scale models can be used for risk safety and environmental assessment to avoid accidents, and for mitigation or remediation of accidents and disasters. So this gives a general motivation for what we're going to talk today. So when we talk about new models or new multiphysical and multi-scale models, we talk about very advanced technologies that are available today. So let me show here a very simple simulation here, just a water column collapsed. So what you see here is just solving the normal Navier-Stokes equation, in which here we have a mesh that adapts to the physics. So with this we can actually capture the detailed dynamics of the system. So this green line here, this green surface here, is actually the surface of the water. So just an isosurface of the water. But you can apply the same technology, exactly the same technology, to other problems. So, for example, this animation here originated a few years ago, part of the DAPL project, in which we released contaminant, a passive trace contaminant, in one street in central London. So we match this simulation against an actual experiment in central London. So this is near the Baker Street. So what you see here is basically the mesh adapting around. So you see buildings, part of the buildings, and how this contaminant actually, or this pollution actually disperse across the street canyons. We've done a very similar experiment in the same region. So that's Marylebone Road in central London. So now here you have two set of cars moving in opposite directions. What to see here, this in blue, is the velocity vectors, and what you see here is basically the pollution from the exhaust of these cars being spread over this region here. So we've done several of these similar simulations just to make sure that we understand how pollution actually disperses across the domain. We can also apply the same technology for solids. So here is a couple between solids and fluids. So these two pillars that we can actually model how the wind can impact on these two pillars. Okay, sorry, same animation. Wave breaking. So here in this case you have a solid structure, so the coastal defense, and how it's smashed, how the wind is smashed against them. So at the same time you can see the mesh adapting around the coral locks, so again the coastal protection. Okay, now that you've seen some examples, let's come back one step. We've seen here a few examples, and you can identify 5 or 6 different physics. So we've seen fluid mechanics, solid mechanics. There are chemical reactions. I haven't seen any example here, but you can imagine chemical reactions are important as well. Thermal transport, so when thermal energy is crucial for the event, and radiation transport, mostly when dealing with nuclear reactors or nuclear systems. Multiphysics is just part of the problem. The other side of the problem is multi-scale. So here is a oil. So basically, this is a pipeline linking the oil field in Saudi Arabia. So in Saudi Arabia there is these huge oil fields, but if you look at net in some scale, you're dealing here with what happened in the pore scale, so the nanometers and kilometers scales. How you can model, how can actually represent these different scales in the system. The same thing happened for the nuclear system. So what you're dealing here is going from the atomic scale, micro scale, mesoscale, component scale to the field and system scales. How you can actually model this and how you can integrate this model. If you look at the nuclear side, this is part of the nuclear core of a reactor, and inside this nuclear reactor that's 4 or 5 meters, from 3 to 4 meters of diameters, the fuel assembly just like 21 centimeters. Inside each fuel assembly there is a few rods, just a few millimeters. Inside few rods, few pellets, again millimeters, and then triso particles, just 1 millimeter. And inside this there is the uranium that's active there. So that's in a nanoscale system. So how you can integrate all these systems. If you move on to reservoirs, the same thing will happen. So from the pore scale, so you're dealing with 10 to minus 7 or 8 meters scale, to the field scale when dealing with kilometers or kilometer scales. How can we integrate this? Efficient models can do it. So we've seen part of the story. So let's have a look on these more details. So for fluids, there is 2 different sorts of models. One is very generic, so very sophisticated, specialized system codes that deals with the physics of the problem. So they are mostly rely on empirical correlations. So they are fast and well validated. So they've been around for a few decades, but there is no detailed dynamics. There are CFDs and CMFDs, so computational fluid dynamics or computational multi-fluid dynamics models, just like CFX, Fluence, RTD, OpenFOAM, etc. They give you very detailed physics, they're very detailed simulations of the physics of the problem. They are very accurate, but they are very CPU intensive, so it's a very, you need large computers to actually make good calculations. If you look at the solids, it's a very, very similar word. So there's two kind of models nowadays, or there was two kinds of models nowadays. One is called discrete element method that track each component, each solid component across the domain, and there is the finite element approach in which you can model the particles, the force within the particles. And there is also what we call today the FEM-based models, which actually couple these two parts. Application for this, there are many applications, from material performance, assessment for failure, like mechanical failures. One good application is this. So this for a FEM. So here what you see in the boat, the colors in the water here represent the velocities, and the color in the boat represent the stress of the material in the boat. So these are two-way coupling in which the water will feel, in some sense, the forces that the boat exerts into it when the boat is meshed, but the boat also will feel the stress when the wave hit the boat. Radiation transport is also another multiphysics models, and there is two major schools on this. There are the probabilistic models that are very accurate but slow. So again, it tracks particles within the system. And there's what's called deterministic models that actually solve integral differential equations. They are less accurate, the first one, but they're faster, and they provide detail on the flux and reaction rates over the whole domain. Chemical reactions are also part of the multiphysics framework, and there is several different applications for here, from nuclear reactors to subsurface chemistry. So in the end of the day, we know nowadays that multiphysics and multi-scale models can help on the design and optimization of equipment, buildings, and facilities. That's been used for quite a while. So everyone who follow motor race, and in particular Formula 1, knows how wind tunnels and virtual wind tunnels are critical to design better cars. And the same thing will apply to every single industrial equipment or facility and process, but also when you're dealing with natural processes. Turbulence and structural integrity in subsea facilities, wind farm, power plants, nuclear reactors. So safety on these facilities are crucial, and therefore detailed simulations are paramount nowadays. You also are very familiar with weather forecasts that use multi-scale models as part of the core, airflows indoor environments. So it's part of our comfort in our houses. So there's models for make sure that houses are better designed, ocean circulation, atmospheric flows, and this list is quite long. But then when looking at all this, you have to remember that these may happen. Pollution, accidents, not just the very well designed new facilities or well designed process, but accidents will happen. So risk and environmental safety is crucial, and it's is part of the multi-scale and multiphysics models play a core play in this aspect. Air pollution in urban street canyons contaminate of surface water bodies. But there is also another aspect that's being exploited over the past 5 to 10 years. These are predictive tools. So how to use new predictive technologies to help design, optimize facilities, equipment, and buildings, but also to help risk environmental safety assessments. And these sort of tools that links advanced fluid dynamics and other models that we're going to talk later on are critical nowadays. So when you're dealing with challenging porous media flows, and that's because my current research is mostly in porous media flow, there are several challenges nowadays. When you think about life cycle assessment, that's not just for oil and gas, but we can also be looking at the water resources. Enhanced oil recovery is part of the problem. So it's part of the challenge. So how to improve the oil recovery in a safe way. And the same thing can be applied to geothermal energy, so renewable energy, and for EOR CCS. So how to actually inject, for example, CO2 in the subsurface and at the same time obtain oil. So part of my past research was on looking at this. So how after injecting a fluid in the subsurface, these fluids is produced, at the same time the fluid that is introduced can stay there. So what you see here is a blob of something. So for example, water here, and inject water from the left hand side. Our objective here was looking at fluid instability, in particular for viscous fluids instabilities. Flows in fractures, so that's crucial when you talk about geothermal energy, oil and gas recovery, but also when you talk about water resources. So how to model fractures here, very idealized system, but you can imagine how when you can transpose this to a more realistic set of fractures in porous media. Again, the same technology that we saw before of mesh adapting the system is applied here, and here is a two-phase system. So there's a fluid here, and we basically inject another fluid. So you see here the mesh adapting as the physics evolves, so it will adapt just in the interface between the two fluids, the existing fluid and the new fluids. So these are some of the research challenges nowadays. How to model with accuracy multiphase and compositional flows in heterogeneous and fractured porous media. In particular, when you apply this to very challenging systems like the HPHT system. HPHT stands for high pressure and high temperature systems. So fluid dynamics in constrained regions, so fluids in pipes, fluid umbilicals, stratified flows, sloshing in LNG tanks. So nowadays LNG tanks or LNG big boats are being transported across the world, so how to make them safe as possible and more efficient as possible. And there is several challenges here. So fundamental understanding of laminar and turbulent single and multiphase flow dynamics is still a big challenge nowadays. The geophysics, we're dealing here with solid mechanics, and What we want in the end of the day is making sure that as a system, as the porous, as the geological formation is fractured, how it will, what's the impact on the environment. So everyone have heard about fracking, I hope so, and what's the impact of fracking in our society. So what you see here is a simulation of the fluid being injected and goes through a fracture, but then because the pressure of the fluid, it is translated as a stress in the rock, and the rock starts to fracture. So this is a typical, a kind of example of a fluid and solid coupling, a multi-fluid and solid coupling. So this is about subsurface characterization, so how you can actually characterize subsurface. So that's another challenge nowadays. We know something about, you have very limited data on the subsurface, but you want to know more. If you want to model this or have simulate this or predict how much resources you can explore, we need to have more information. And one of the fields, excuse me, one of the fields that's it's very, very important nowadays is on upscaling or reduced order models applied to this. So what is this? This is basically how can someone generate a very fine scale model of the geological formation, and how these fine scale that cannot be simulated, because then you need a really large cluster, computer cluster, how we can reduce the number of degrees of freedom of the system. So then to apply reduced order models. So the challenge nowadays is how to better implement geomechanical models, how to coupling geomechanical models and multi-fluid models. That's a big, major challenge nowadays. Any part of exploration, there is risks associated with the exploration. So some of the risks are quite well known for the oil and gas industry. So hydrates formation in pipes, asphaltenes and walks formation also in pipes and in the geological formations. Uncontrolled water production. So and this basically means when there is a break in the cap rock and water from other formations come to the reservoir. But you can think about this as the other way around. So how can this oil and gas start contaminating the water reservoir? And you can think about this as also strategies for mitigation or remediation of problems. How can these sort of models help? By new sensor technologies, minimizing the heat and pressure losses, chemical inhibitors, and other chemicals to help prevent contamination from both the oil reservoir and of the water reservoir. So one of the very, very cool new technology nowadays, or now technology that's being developed nowadays, is the concept of optimal sensor location technology. So instead of having several sensors in an experiment, you only allocate sensors where it's really necessary. And simulation can help you actually identify where these sensors need to be placed. And you can extend this to oil and gas or to water resources systems, and actually locate sensor just where you want, where it's necessary. This technology is now being being researched for location of CO2 sensors for CCS. So what is the new, what I consider to be the directions of the multiphysics, multiphase, and multiscale modeling in porous media list. Multi-scale, from pore to core to field scales. How you can integrate all these scales. That's a big challenge. And there are several aspects here that need to be taken into account. Fluid rock interactions, we've seen some of this, so formation of fractures. Flow regime transition, so flows in the formations are obey the Darcy law, and then as soon as it goes to the fractures, it becomes a Navier-Stokes law. So how can you integrate the model to take this into account? Impact and productivity. I'm going to talk about later about the flow instabilities, but this is a big thing when we think about the productivity of oil fields, because flow instability have a huge impact on the efficiency of production. Not only this, fracture formations. Part of the production of oil and gas is from natural fractures but everyone has been seen nowadays, heard about nowadays about fracking technologies, and that's basically includes fracturing the system, the geothermal formations. If you move to the geothermal energy system, fracture of the formation is crucial. Otherwise, you cannot produce heat. You cannot produce a fluid with heat that's necessary for generating electricity. Predictive science and technology for risk management. So that's a critical point. How can this model help on predicting safety and environmental risks? Sense technologies is one approach, so that's part of this story. So better sense technologies that are accurate, mobile, and have a good response time. Emergency response system, rapid models to support accident scenarios. So when there is an accident, you don't want to run models or perform simulations that run in 10-15 days or a month. You will need models that can be run fast. So there are technology nowadays that you can run different scenarios very fast. More accurate predictive models for production. So there are new technology for history matching and data simulation that need to be embodied in the models today. So what is this in the end of the day? How we can get information or field or experimental information or sensor information from the field itself and feed into the model to make sure that you can predict what's going to happen in the near future. So we can see these nowadays mostly in the weather forecast. So every day there are data from different sensors across the world that feed the models for the weather forecast models, and then helps you adapt the forecasting as you go. So the last part of this talk, and I apologize for the time up to now, I will talk about my current research within the icy first fluidity. So fluidity is an open source finite element method based dynamic core that is used for multi-dimensional compressible multi-fluid system. Okay. So being used and validated against a range of applications, from subsurface flows, wind, urban air pollution, ocean modeling, and you name it. One of the major features of fluidity is the mesh adaptivity library that I've showed you before, that we focus resolution where it is necessary. Fluidity has been tested to work in parallel, so it's been nowadays working in the largest supercomputers across the world, in the US, in the UK, in Europe, in Japan, with success. So there is scalability on fluidity, and we changed the way that we think about software a few years ago. So fluidity has potentially 20 to 30 years old. In the beginning, we design every single element of the model. So from the I/O, so input and output, visualization, solver, preconditioners. Nowadays, we just get what's better across. The only thing that's ours, so from the fluidity itself, is the dynamic core. So how you discretize the equations and how you solve the equations. Everything else is you get use open source solutions. So for example, for solvers and preconditioners, we use PETSCI. For visualization, mostly use ParaView. Both of them are open source. So it's been tested against standard CFD tests. So collapse water column I showed before, flow past a backward step. So that's basically when you inject a fluid, two fluids, and there is a step there, so you can see the vortex. So that's just a zoom for this long channel here. So you can see here how the vortex formation occurs here. So there is an edgy velocity on these regions here, so they can actually capture this, and the way to capture this is through mesh adaptivity. So that's you see here that where there's no physics, so mass is still large, still very coarse, but when it's necessary, just adapt the mesh. But not just this, we can send this to several processors. So this is a node simulation, so that's 10-15 years old. So this was done with 16 processors here. So nowadays we are dealing with a few thousand processors in large supercomputers. So our overall aim for a fluidity team is to develop a flexible, unstructured mesh and numerical robust, FEM-based, computational multi-fluid flow dynamics solver. So that's our aim, to actually develop something, a solver that's robust, numerically robust, and flexible. Talking specifically about flows in porous media. So I have another talk for flows in pipes, flows in environment, and I can talk about this later on, another opportunity. But today is the focus on porous media flows. I just choose slide on the numeric itself, the core numerics. So what's really important here is that the use of finite element method that is merged with the control volume method. What this mean? It means that for every single element here, so the blue triangle, we have several control volumes. What we're doing here is basically linking finite volume method and finite element method. Finite volume method is great for mass conservation, and that's what we want, but it's not very accurate. Finite element methods is known by the accuracy, numerical accuracy of the method itself, but it's also known that it's very dissipative, so it's not very good on conserving mass. We merge both of them into what's called the CVFEM, control volume finite element method, to make sure that have the best of both worlds. Not only this, these sort of element types that you see here, it's called P1, DGP2, so linear discontinuous in velocity, so that's the red balls here, red circles, is linked to the continuous and quadratic representation of pressure. So what this represents is that our element type can give us a very good accuracy, numerical accuracy when calculating. So all quantities that you calculate within every single control volume, that is then translated or extrapolated to the finite element space. So calculate all the quantities in two different spaces. I'm not going to bother with all this numerics, just say that this is the equation that you solve for. So now that the Darcy equation, So that in which the sigma here is a representation of the saturation, permeability, and relative permeabilities. So we can imagine that permeabilities are actually tensors. So it's a really, really big quantity here. The other equation to solve when you're dealing with multiphase flows in porous media is saturation equation. So this is the saturation equation that we solve for. So here's the porosity of the system, saturation and velocity, and the source term. So when you couple both of them, you can calculate three quantities: velocity, pressure, and saturation for all phases. Remember that velocity has a number of components relative to the dimensional algebra problem. So it's a 2D problem, so there's 2 velocities per component for phases. And if there is 3 dimension, there are 3 velocities per phase. So our aim on this particular study is to understand the flow instabilities in immiscible fluids in heterogeneous porous media. We know from the theory that as soon as you have 2 fluids of different viscosities, fluid instability will start to occur, and you generate what are called fingers. In oil and gas production, these fingers can impact negatively in the production of hydrocarbons because it decreases the sweep efficiency. In geothermal energy, these sort of problems or these sort of problems may occur, but it's not that relevant. And you use several families of element pairs. So that's called PIDGPJ, PIDGPJ-DG. So this is discontinuous for velocity and continuous for pressure, discontinuous for velocity and discontinuous for pressure. So these are 2 different families of element types. Why is this important for porous media flow? Because the occurrence of fractures. So you need to make sure that large gradient of permeability can be captured by the system, because these gradient of permeability will have an impact on the flow itself. Viscous flow instabilities arise from different sources, but mostly is because the difference in viscosities of the two fluids, the 2 or more fluids, and they are triggered by heterogeneities. So this one simulation. This is a hello shot cell. So what you see here is a 2-dimensional problem. And there's a source here and a exit of domain here. So a sink term here. There's 2 cases here. One is a homogeneous case with a permeability of 10 to minus 10 to power of minus 10 centimeters square, and one it's heterogeneous with permeability ranging from 10 to the power of minus 12 to 10 to the power of minus 10. So in the homogeneous case, we test against viscosity ratio number equal to 3 and viscosity ratio equal to 10. So this for viscosity ratio equal to 3 and equal to 10. So this for both homogeneous, so there is just one constant permeability. Source term here and sink term here. So because the pressure gradient, the fluid goes from the source to the sink. The simulations are not synced in time, so this time here is not a matter, it's not a problem. But you can see it's an initial formation of fingers as it goes. So these are formation of fingers. However, you can look here for the 2 cases that we saw before, and I just repeat the same case but using a heterogeneous system. You can see that the finger formation is much more pronounced. So there are regions that in which the system remains. So what you see here in the end of the day is a low efficiency on removing the blue fluid that was here before the system. So what you can see here is a representation of saturation as it goes. So this is part of a study that was published last year from one of my PhD students. And we basically validate the whole model against experiments to make sure that everything actually works as it's supposed to work. And then one of the part of another student is actually looking at this in more detail for a large three-dimensional system. So the other part of my research nowadays is focused on reduce all the models for permeability upscaling. So a major issue nowadays is try to understand how you can upscale permeability at the same time you keep the statistics intact or almost intact as you reduce the number of degrees of freedom. So upscaling basically means a reduction of the degrees of freedom of the system. So upgrading, so it's basically mesh coarsening and upscale. So field homogeneity are common methods within the porous media flow sector. So, but the problem is most of these upscaling is based on experience. So it's been around for oil and gas industry for a large period of time. So for 20, 30, 40 years. Most of the upscale is just done by experience itself. There isn't much systematic technology behind it. What we're proposing here is to reduce all the models for addressing this permeability upscaling. And that's what we're trying to do here. So this is part of my ongoing research. My student is finishing these simulations, and hopefully in a few months we can show more interesting animations. But this was his first set of animations. You have here a system that is saturate one fluid, and the system is divided in 4 regions of different permeability. So this is because you want to benchmark against existing physical experiments. The flow comes from the left to the right, so we know that the system is in blue, the regions in blues have a lower permeability, so the flow is going to be very, very slow, whereas the regions in reddish, they have a larger permeability, which basically means that the fluid is going to run faster. So that's a reference solution. So there is 17,000 P1 to GP2 triangular elements. As expected, the fluid here is faster because here a region of large permeability, but here the region is of lower permeability, so the fluid trends to go to this region here of higher permeability. So this is called cross flow in porous media. The same simulation with arithmetic mean. So in this case, the mass reduced to 2000, and the permeability field is average over this region. We can see the same features, but not the same details. So the cross flow is not very clear how it happens here. It seems there is some cross flows also in this region here, which is not completely true, but from the reference simulation, but that's what we capture. So because the system here has a much less degrees of freedom, so simulation run much faster. If you apply statistical methods or random methods here to generate the permeability field, you can see a very similar behavior as the arithmetic, but there are some patches saturation across the system. but in general, the qualitative solution is very similar in both cases. So overall, simulation the dynamics is similar. Cross-flow is not really cannot be observed in total, and when you start to looking at the quantitative solution, there are some discrepancies on the quantity of fluid that is obtained. So what my students are doing now is actually applying what's called high order singular value decomposition, so different methods. It's more rigorous methods for reduced order model, and linking it with machine learning technology, but now not applied for just a scalar as a permeability field, but applying to anisotropic permeability tensor. We use for this case the what's called SP10 benchmark, so the system does already know all the quantities. The reference case here contains 600,000 cells, so that's a tetrahedral system, so the 3D case, whereas the upscale or the reduced order system has just nearly 2,000 tetrahedral cells. So what you see here is basically the permeability field. So there varies from 10 to minus 7 to 1 millidarcy, and this is the saturation at one instant in time. So this simulation is still being running in a parallel system, parallel computer, so it takes nearly a month or more to actually run the whole thing. And for a simplified case, so using the upscaling method here of 2000 elements, you have a more patchy probability, just 2000 elements, so the representation probability is much lower, but you can see here that in some sense there are some similarities of the saturation field at the same instant in time. As I said before, this is still ongoing research, so my students still running this problem as we talk. So hopefully in the next month or so we have solutions for the final solution with more quantitative solution for this system. But I think it's quite cool to actually show this result as it is now. And if you notice here, it's a huge difference. We talk about nearly 300 times less elements in the system. So, sorry, this one is still running, so it's running for more than a month, and this actually run the full simulation run in a few minutes. So that's a huge difference. So just final remarks. So advanced multiscale and multiphysics models are crucial for design optimization and of industrial process and facilities, safety environment, impact assessment, that will support mitigation and mitigation procedures after accident and disasters. So it's something that's been happening nowadays, but also is supporting effort for energy transition. So there's a number of research work nowadays on how to make transition from fossil fuel to renewables much smoother, as smooth as possible. Technologies I mentioned today from fluidity IC first, they use these overlapping CVFN model of different elements, the element types. Has been work that has been research on viscous fingering, but that's not just this. There is a lot of more work being around this new technology. Efforts being put on raw methods for flow dynamics, and the next step of this research is going to be model optimization and continued validation against experiments and field data. Thank you very much for your attention, and I hope you enjoyed. And if you have any questions, please do not hesitate in contact me through my email address or my Twitter. I try to respond as fast as I can. Thank you very much.